Islem, Rekik. So are you from
Imperial College?
From Imperial College, sorry. And she will tell us more about predictive intelligence in network neuroscience. Thank you very much.
Thank you. Thanks, everybody. Thank you for inviting me. It's a great pleasure to be here today. So I hope my vocal cords won't disturb me during this presentation. It's not my best shape ever, but I'm going to try to give you an exciting and clear presentation at a slow pace. So I'm so happy that Jonathan actually has given you a very amazing introduction about synthetic data, particularly in the space of images. So what I'm going to do is take that and extend it to the space of graphs. So in medical image analysis, and particularly when we want to design AI in healthcare, we wanted to collect a lot of data. In an ideal world, you'll have multimodal data. So you'll have, for example, functional MRI, PET scan, CT, diffusion MRI, regular MRI. And there is this hypothesis that the richer the data set, the bigger the data set, the better the diagnosis. So the more, the merrier. However, if you look at this world map, there was a paper published in the Lancet in 2021, and they looked at the number of MRIs, MR scanners, which are used to primarily acquire MR images, right, magnetic resonance images. And you can see that half of the world actually doesn't have these scanners. So it's for example, in the yellow countries, it's between 0 to 2 scanners per million inhabitants, which is very small. I come from Tunisia, for example, and we only have 2 public scanners in the whole country. So that's a very limited number, yeah. So when we want to design our fancy models that work on our, multimodal data, we need to think about half of the world. What about us? What about them? Okay. So attention is transformative. We have seen transformers from a technical perspective, but if we think about transformation from a philosophical perspective, you can think about it that what you put your intention into is what's going to transform our future, will transform society. So also the brain, the way the brain works in neuroscience is what you're attentive to is what you build your strength in. Okay, so attention is actually transformative. So there was a series of nice papers published in top journals, The Lancet, eClinical Medicine, Nuclear Medicine, Communications, who were dedicated to exploring the question of accessing medical imaging in these low middle income countries. So how to improve access. Medical imaging and nuclear medicine, a Lancet Oncology Commission, they were also talking about medical imaging in these countries, how many images we have, what are the data sets that are collected in those countries, what is the representativeness, the fairness, when you compare to these 2 halves of the world, yeah? And so there are lots and lots of studies, and the majority of these studies, they focus primarily on this solution. So the mainstream solution is to increase access to medical imaging. So basically building in new imaging facilities, going to these countries in Africa, South Latin America, and trying to bring the scanners, train people, build workforce capacity, let them, train them to acquire the images, give them infrastructural training, et cetera, that comes with all these fancy imaging facilities. So this is a nice solution, providing the training, et cetera. So, however, I would say that it is kind of time-consuming, labor-intensive, and costly to implement. It's very expensive to bring these scanners, particularly if you have high-resolution scanners. Even in the US, if you look at the PET MR scanners, which acquire PET and MR images, they're not very, very common. So what we want to do, we want to take a new perspective, a new way of looking at this problem. So we, instead of going with a mainstream solution, which requires billions of millions of euros and pounds, we want to design affordable, alternative, and faster solutions that can be deployed in these countries. And that's in an ideal case. So the question that we're raising here is the following. How can we diagnose early and better with minimal resources and at lower costs? And this spans the new field of affordable AI. Affordability is a very looked area in research, and affordability is a multidimensional problem to solve. Affordability comes with data, with compute, with RM, with lots of questions. It's a high dimensional space. Okay, so we're starting with tiny steps and hoping to build more and inspire more people to just follow this. So everybody wants to collect more data. We want less data, better accuracy. So let me just formalize this. So imagine you have an input data, and this data, X, it could be an MR image, it could be a graph, it could be a video, whatever you name it, you call it, it's generic, okay? So this data hypothetically is affordable to acquire, it's accessible. It can be of low or middle quality, which means you have poor quality data, okay? So it can happen, so it's not necessary, but you can have that. And what we want to create or generate is data, X hat, that is actually costly to acquire, inaccessible in many countries or many facilities. And when I say actually countries, like you can be in the UK and not have access to such facilities. So when we design affordable AI, we design it for everybody. It's for the whole world, not just the other half, yeah? So, and also we want to have a high quality of the data. So this is the generic frame, and it's a huge, like it's very abstract, very generic, but I'm gonna give you a tiny example with application to the field of network neuroscience, which I will introduce in a bit. So what we want to do here, we want to solve this problem by learning this mapping function F or transformation from the X space to the X hat space. So basically going from data to no data, and this is more about generating data and predicting data or synthesizing data. So in the field of network neuroscience, usually we start from brain images and we turn images into graphs. So from now on, all that you're going to see is graphs, okay? So how do we do that? I'm not gonna tell you how we do it. It's like a whole field. They're like 8-hour processing or so to get a connectome or brain connectivity map from an image, but I'm gonna give you a brief introduction of that. So if you haven't seen this before, you have the most affordable, I would say, unfortunately, modality to create brain graphs is like MRI. So you still need to go through MR for now. Maybe in the future you won't need that. But this is, our lower bound. So we're starting from there. And we transform the image into a graph. So basically, one of the ways is like to use what we call anatomical atlases. You split the brain into different regions, and then each anatomical region will represent a node in your graph, okay? And the interactions between the regions, they represent, for example, correlation and functional connectivity. Like we say, we hypothesize that neurons which fire together, they wire together. There is a wire, there is a roadmap, a connection between them. So this is one way of looking at connectivity, and you have different types of connectivity. For example, functional MRI, diffusion gives you structure, the infrastructure, morphological gives you the morphology. So you might think about looking at your brain, at your roadmaps from different perspectives, okay? And capturing different aspects of your brain network. And by the way, all of your brain networks are fingerprints. So there are lots of studies about that. So anyways, like affordable network neuroscience. So what we want to do is start from an affordable image, which in this case is actually the T1 weighted MR. And we were the first to create brain connectomes from T1 weighted MR, because in the neuroscience literature, all brain connectivity maps or connectomes, connectomics, omics, genomics, proteomics, all the omics. So in connectivity, it's functional MRI. Functional MRI and diffusion MRI, they're costly to acquire. Usually when you put a patient into the scanner, you acquire the T1 weighted MR and then functional and diffusion. So they need to sit for a longer time. And if they have a disease or they have a stroke, and it wouldn't be comfortable for them. So what we want to do, for example, is to go from T1 weighted MR to diffusion functional. So this is one thing that we can generate. So it'd be an interesting problem to solve. So basically we'll start from T1 weighted MR, create a graph. And then from this graph, we're going to span 3 dimensions. The first dimension, we want to generate graphs from a simple one single observation of a single subject across domain. So cross domain generation. We have cross resolution generation, and cross time, and I'll explain this in a bit. So just remember these three dimensions. So we have published more than 60 works about this, like starting from 2019 to 2022. We've done a lot of works, but today I'm going to give you just glimpses of a few of them, just to give you an idea. So how do you derive a morphological brain network from T1 weighted MR? So if you don't have access to functional MR and all you have is MRI, you still can do connectomics. So if you want to learn about that, you can check these works. So there were like a few works done by my research lab, and like we introduced the concept of morphological networks. So another thing that is very interesting, there was a review paper published in Nature Communications back in 2018. And as you guys can see, when it comes to medical imaging in general, the majority of the works, because it's related to computer vision. So everybody does segmentation, you have classification, you have also detection, some reconstruction of images like MR reconstruction, etc. But prediction was completely overlooked. So nobody worked on prediction at the time. And this was one of the motivations back in 2018 to start kind of digging into this. And we have affordable now, so there's a whole lot to do. So let's start with the first domain, the first predictive axis, which is the domain. So what is the problem that we want to solve here? Imagine we have a graph. So this graph can be anything. Like for me, it's a brain graph. For you, it could be anything else, okay? And what we want to do, we want to learn this mapping, this transformation that allows us to predict another graph in the target domain. So this is the target graph with different connectivities, different properties, etc. Then for the second one, we have the multi-graph prediction. So this is a more complex problem. So instead of predicting a matrix from a matrix, we're predicting a tensor from a matrix. So basically, we're mapping a single matrix onto a full matrix in completely different domains with different distributions and different properties. So for the resolution, to the best of our knowledge, we were the first to introduce the concept of graph resolution. So I give a graph theory course. And like I've looked at different graph methods. Usually we do compression, we do filtering, we do downsizing, but there isn't any, like when we say, for example, image resolution, super resolution, you find many papers, but when you say graph super resolution, you don't find any works along these directions. So in this work, so I will motivate it and explain why it's an interesting problem to solve in connectomics. But basically, just from an abstract representation, we go from a low resolution graph with a few number of nodes to a higher resolution graph where we increase the number of nodes and we try to predict this huge graph or bigger graph from this smaller one. So this is super resolution problem. So now the last dimension is the time. So what is time here? We have an input, a single time point. And what we want to do, we want to learn this time-dependent function f of t, which will map your initial observation onto the future. So we are predicting the dynamic changes in the graph, okay? And we have one final, I would say, it's not a dimension, but it's a concept that permeates these three dimensions. And this concept is the concept of template-based learning, which we also have introduced. It's like one-shot learning. So I'll give you an example later. So it's called graph integration. So imagine there are lots of methodologies for data integration, data fusion, and data integration and fusion is very interesting when it comes to learning representation of cohorts, populations, doing comparative studies, et cetera, et cetera. So here in an abstract way, what we have different samples. Each sample is represented by different views. These could be different domains also. So functional domain, structural, morphological, or so you guys name it. So basically each subject has different views. And what we want to learn is a mapping that integrates all these tensors, multimodal, highly heterogeneous tensors into a single template that is a fingerprint of this whole population that captures all the variations that are there and enables you to fingerprint a whole population of tensors, okay? So we solved this problem too. So I will give you a few examples in a bit. So at the end, what we're starting from a single observation, and we are predicting new data. And hopefully when we use the new data with the generated one plus the original ground truth one, we will be able to predict better reproducible biomarkers. We will be able to do better classification, increase the classification between disordered brains in normal controls, et cetera, so generating for improving AI in network neuroscience. So all of these works are published. There are lots of works, so I'm going to randomly sample 3 examples. Yes, go ahead. So the domain here, it could be a different type of graph. So for example, you can have functional connectivity for using functional MRI. So it kind of models the correlation in the functional activity in the brain. So we use bold signal, blood oxygenation level, and we measure it over time. So this is the signal, how much oxygen your brain takes in a single tiny, teeny voxel. And you have another voxel in your brain, and you measure the bold signal through this functional MRI scanner, okay? And then you compute the correlation. That's a type of connectivity. So that's one domain. Another domain, it could be, for example, looking at the shape of the brain as a shape, and then comparing the shape of 2 regions and say their morphology is similar or dissimilar. So basically, you can think of a domain as a different measurement or a different attribute, okay? So that's one way of doing that. The number of vertices, it depends. So yeah, the number of vertices, we are using an atlas. So I'll give you a few examples later. So it depends on the anatomical template we're using to split the brain into different regions, okay? But these are very generic, generally. So here we have the same number of vertices for now, okay? So yeah, so moving forward, all these works are available if you guys want to learn more about the math, the details, the codes. We have more than 39 presentations on the Basira Lab YouTube list. We have 20 GitHub code video demos. We were great supporters of open science. So if you want to run the code, you're struggling, you can just go and see how you can run it. And we have more than 54 codes also published, open science. These are generally by undergraduate and graduate students. So we try to push forward the open science, but it doesn't mean that the code is perfectly done. So if you have a problem, contact the first author. Okay, cool. So all of these works have been recently published in the TPAMI paper, So if you're interested in getting a full grasp of these 3 dimensions, graph neural networks and their application to network neuroscience, feel free to look at the Pattern Analysis and Machine Intelligence journal. So the paper is already out there. Okay, so just to keep it simple, stay awake, don't sleep through. I know it's the end of the day. I'm going to give you 3 examples, 3 slides animated to just give you the gist of what we're trying to solve here. So first, I'm going to start with cross-domain prediction. So this was a paper accepted in MIKAI 2020, and actually was the first paper from the continent of Africa. So, and we want to see more, hopefully in the future. So what is the problem that we're solving here? So basically, the problem is like that. Given a single brain network, how can we learn to predict the brain connectivity map and across different domains? So for example, for morphological, we're trying to get other types of connectivity. And here we were the first to design a graph neural network that solves this multi-target domain prediction. So the existing works at the time, they didn't solve the multi-domain prediction, which means usually existing works go from one single graph to one. So it's one-to-one mapping, but this is one-to-many. Okay, so that's what we're solving. And the existing works back in 2020, they overlook the topology. So we know that when we work on graphs, they have topological properties. So here in our loss formalization, we added some topological conditioning. So let's start from the beginning. So here we have the source domain. We have n subjects. These are different subjects. And then we have the target domains from in domain 1 to domain M. So all of these data sets are available, which means we have ground truths, okay? So everything is available. We're going to train our model. So what we do first, we build what we call a feature matrix. So we take the graph and we take the edge values, and these are the connectivity weights. And by the way, all of our graphs are weighted undirected. Okay, so we haven't, for example, generalized these models to directed graphs. So everything we work on is like weighted undirected. And then we build a population graph here S. So this is a similarity between subjects. So we have 2 subjects here, and then we calculate their similarity, to model the similarity between different samples in the source domain graph. And every node has the features as the connectivity weights in the brain. Okay, so that's how we're doing that. So this is vectorized into single line. It's the feature for each node, and each node is actually the subject themselves. And we do the same for the other target domains. So morphological, for example, type 1, type 2, type 3, etc. So after that, we formalize our learning model as a multi-graph GAN. So I'm so happy that Jonathan gave you an introduction about GANs. So here what we have, we use an encoder network. So the encoder network takes the feature map and the subject similarity matrix, and it learns an embedding for all these subjects. So there is one thing here though. So we know that the source data can be highly heterogeneous, and we notice that when we have like multiple like heterogeneous data, the training of the model might collapse to a single mode in the target domain, and you won't have a representative learning of your multimodal, you know, like your multivariate distribution. So one thing that we introduced here is to cluster the data. So how do we do the clustering? We use the embeddings to cluster. You might ask me, okay, you're using the embeddings, how do you get the embeddings? So what we do, we have a generator network. So encoder, decoder, we train it for a certain number of epochs. Then after the loss is regularized, like you have a good training over there, then you cluster these embeddings into different clusters, and then you connect them with a set of decoders. So here we have for each cluster, the pink cluster, we have M domains, okay? So we do what we call a cluster-based learning, which means we disentangle the distributions in the source domain, and then we map every single source graph into its target domain. So from morphological network in cluster 1, we predict multiple networks in the following cluster. So this is the basic idea, but there are lots of layers, guys, and there are lots of math, so I'm just covering the basics. So here, basically, this is an encoder network and a decoder. So you encode, have an embedding in low dimensional space, you decode through cluster 1, cluster M, and all of these decoders across all clusters that are regularized by a single discriminator network. Okay, so this is one of the contributions. The second one is having a topological loss. So we know, like for the brain network, you have two matrices. So let's call the matrix, for example, adjacency matrix X and adjacency matrix X hat, the predicted one for one single brain. So if you take the L2 norm, the distance between them, you're just comparing connectivities, but you cannot have an idea about, for example, the hub nodes. Do you guys know what hub nodes are? Central. So hub nodes, basically, when you have a node with which is connected to many other nodes. So let's say I'm connected to 10 of you, and you are connected to 100 of them. So you are a hub node, like you have stronger connectivity than I am in my network. So when I predict the network, I should not only compare the weights of the edges, but also the topological power of every single node in the network. And that's what we call topology aware learning. And this, this is a part of graph theory, okay? So once we do that, so we added a topological loss to enforce this consistency in topology between the predicted graph and the ground truth one. And then basically at the end, these are the results. So we had 310 subjects. We use different, we have four different morphological attributes, and including the primary one. So different types of morphological networks, like brain network derived from maximum curvature. So you can think about it different domains. So just to cut it short, and then here you guys can see that we didn't have any benchmark because we defined the state of the art. So the first model here, adapted MW GAN, was primarily designed for images. So we adapted it to graphs, and we used graph convolutions because you cannot use regular image convolutions, right? So we needed to adapt that. And then you can see that without clustering, we get even worse results. But with clustering, when we added the clustering, the disentanglement of the source space, and we added some topological enforcement. So this is multi-graph GAN, where we use closing centrality as an additional loss. between a centrality and eigenvectors. These are different types of centralities that tells you, that quantifies how central is the node in your network, how important is the node. So if you have different roadmaps, I would assume that Rabat is like a central node in the roadmap of, you know, like transportation in Morocco. Yeah, so you can think about it that way. And you guys can see that when using these two topological losses, additional losses, we got lower MAE, mean absolute error, across different topological measures. So we also evaluate the topology, but we also got high PCC. So anyways, like this is the key idea. We try to solve a problem where we're predicting multiple graphs from a single graph using a adversarial learning with cluster disentanglement and topological measures. So you have a 20-minute video online if you guys want to learn about this in detail, and the code is also available on GitHub. So now I'm going to talk about this, and this is, I think, this is more important. This work excites me more because it's a very interesting problem to solve, the cross-resolution prediction. So basically what we want to do is like having an initial graph, we want to learn a high-resolution graph like this. How can we super resolve graphs in general, but here we're working on brain graphs. So just going forward, so this work was also the first from the continent of Africa to be presented in a top conference called IPMI, Information Processing Medical Imaging, and it's highly selective. So this was presented by my PhD student Islem, and the title is like non-isomorphic intermodality graph alignment and synthesis for holistic brain mapping. Sounds complex, but let me simplify. So what is the problem we want to solve here? If we go back to this, so let me explain how we do this in medical imaging. So you guys remember the images? We start from images. For the images, you need to kind of, you know, segment them into different regions. So image registration, segmentation, processing takes many hours. So to generate the brain connectome at this resolution, let's say it might take 4 hours, but at this higher resolution with fine splitting and partitioning of the brain into smaller anatomical regions, it might take double the time or even more. So this is very costly to process from the images. So what we're trying to solve here is to circumvent the need of acquiring the image. We don't acquire the image, the modality at all. We don't need functional MRI. We don't need diffusion MRI. And we don't need the processing time. So we just use 1 second to test the network and get the connectome and the graph in that target domain immediately and at a high resolution, okay? So it's very affordable. So here, the existing works generally, when they try to generate graphs, the graphs are isomorphic, so there is like preservation of the neighborhood, and they have the same number of nodes. Okay, so they use the same number of nodes. So the existing works also do not look at the domain shift between the source domain, where we have the original source graph, and the target domain, where we have the target graph. You can see the shift right here. They're not aligned. Functional distribution would be different from morphological, for example, okay? Grayscale images will be different from, I don't know, color images. So what we wanted to solve here is solving two problems at the same time. The first one is going from a small resolution NR by NR matrix to NR prime by NR prime adjacency matrix of a graph. And the second problem we wanted to solve is to align the distribution, solve this domain shift between these two spaces, okay? So what we proposed is IMAN graphnet. So IMAN graphnet basically is composed of two learning blocks. In the first block, we introduce what we call an aligner graph neural network, okay? So this aligner network is an intermodality aligner, which means you take the source modality and then you try, which is the graphs, okay? And you try to align their distribution to that of the target modality. So in this example, we design our aligner network where across the number of epochs as you train it, you go from the pink here, the purple here is the distribution of the source domain. The target is the blue one. And as you keep on training, the output, the source graphs here will shift towards the distribution of the target. So it gets S to T, okay? And this is the output of the network. So the network will align the distribution of the source to the target. So you might ask me, Why would I do the alignment in the first place? So you want to basically, for each source graph, you want to predict a target one. If they are living in a completely different spaces, that's a difficult problem to solve. But if you map them and you align their distributions, it will be straightforward and easier to do the prediction. So here what we did, after we aligned all of these graphs, now if you plot the distribution of their edge weights, it will be aligned to the target one. So the purple is aligned to the blue. And then we take these X hat S to T of subject 1 to subject N, training subjects, of course. We do this subject-wise training. And we feed them into a non-isomorphic intermodality again. So this is basically also generative network where we're simply playing with the dimensions here. So it's not fancy science. There is still a whole lot of work to be done when it comes to super resolving graphs. But we have adopted a very quite simple approach, I would say. And basically the output to this simple, generator network is the graphs of resolution NR prime by NR prime, which are the predicted ones, X1 target hat. Okay, so first thing, align the distribution. Second, do the prediction. So that these are two steps that we adopted in this IMAN graph network. And for our results, I'm going to show you quickly what we have done. So we used a public data set where we had 150 morphological connectomes, adjacency matrices of size 35 by 35, so it's small matrix. And we tried to predict matrices of size 160 by 160, which is functional connectivity, costly to acquire. And let me show you the results here. So first, we took IMAN GraphNet without any alignment. We completely stripped it out of this alignment. No alignment, just prediction, training a simple network, generating a graph from a graph with super resolution, of course. And then the second one, the purple one, we used a prior alignment. So we didn't do it in a back-to-back learnable manner using a neural network. We just pre-aligned using simple statistical alignment, and then we fed the aligned data independently to the network. The green one here, we also introduced additional losses. I'm not talking about them here, but we had a Pearson correlation loss between the target ground truth and the predicted one. And then we have topological loss also. So these are ablated versions where we remove the Pearson loss and the topological loss. And then we have the IMAN GraphNet, the final one. And you guys can see using two-tailed PRT tests, statistically this was significant. So we had the best model here, the yellow one outperforming all the ablated versions and comparison methods. Yes. The y-axis, very good. So here we have the MAE, the mean absolute error between the predicted matrix and the ground truth matrix. The second one is the MAE, mean absolute error between the closeness centrality of ground truth matrix and predicted one. Closeness centrality, this is topological evaluation of the network soundness, biological soundness. And we have here betweenness centrality, and here we have eigenvector centrality. Three different types of centralities.
And the first one, does that go from 0?
So that should be, I didn't put the scale here, but it's a residual. So it should be between 0 and 0.5.
So what I'm trying to understand is how can you predict things? You shouldn't be able to predict going from the smaller resolution to the larger resolution. You should be able to predict the distribution of possibilities. Because there should be more information in the larger resolution than the smaller.
Yeah. So here we're evaluating the larger one. So we're evaluating the outcome of the network. So this is just a difference of matrices over the number of testing samples.
I don't understand how the problem is possible. That's what I mean. There should be more because you add into data, you have something with lower resolution, therefore you have low amount of information.
Yes.
And you're going to try to high resolution where you have high amount of information.
Yes.
So any transformation to your delete information, you shouldn't be able to add information. How come you don't have a distribution over possible graph with higher resolution? The same way that if I give you a low resolution image,
right,
you should be able to give me like a distribution over a space of possible higher resolution, but not a single higher resolution. No.
So here it's a data-driven approach. So we're learning from existing examples. So like all this training, what the network is learning from is the training data that we're feeding into it. So the distribution will be drawn from the training data. So whatever the GAN is learning here in the super resolution network, it's learning by just comparing the bigger matrix to the predicted one, and it's optimizing the loss based on that. So this learning process basically is constricted by the data that we're giving to it. Does that? And for the test, so we're using cross-validation here. So for the test, basically, it's quite simple. So once you have this network, I have a testing sample. So let's imagine this is a testing sample. Okay, it's a low resolution graph. I feed it into this one and I align it. Then I feed it into the next one, and then I'm going to get its matrix right here. It's bigger matrix. So then I have the ground truth super resolved graph, right? And I have the predicted one by this architecture. So I'm just going to compare their residual.
And this error that you're showing us, are these on the test set or on the training set?
No, test. That's on the test set. And here, actually, we compared, sorry about not super resolving this, it's a very small image. So we compared the top connectivities for subject 1, for example, of super result. My pointer has just not there, sorry. Yeah, so here, so if you compare these, we have reproducibility of top connectivity. This is a connection in subject 1, high resolution graph ground truth, and this is the predicted one by our network. So we have a high reproducibility in top strongest connectivities using our network, which means it is kind of working. We're not just hallucinating. Yeah, so we have a lot of extensive clinical validation that's not included here. It's a long study, yeah. Cool, thank you. So, yes? Pearson correlation, it's correlation basically, because we use it in functional connectivity. How do we get the functional connectivity? We take Pearson correlation between the bold signals. So it made more sense to kind of introduce such a loss, yeah, sub loss. Okay, so the paper also is like the video is available, long video with all the details on YouTube. We have a long playlist of the publications, and the code is available online. So now the last example that I'll cover quickly is Crosstime Prediction. So Crosstime Prediction, we have also lots of works trying to predict the evolution of graphs, which means the changes in the weights of connectivities between nodes, the changes in the weights of the edges. So what is the problem statement here? So given a baseline brain graph, we want to learn a time-dependent mapping that allows us to predict the evolution of this graph over time. And as you guys know, how do we get the ground truth graphs? These observations, we need to have an MR scans, right? So we take an image, we transform an image into a graph, but this means that we have a longitudinal data. We have a time-dependent data. Otherwise, you can't do training of such models, okay? So the question that we want to solve here is how to predict the evolution of a graph over time in a federated manner. So before federated learning, we have solved this problem. We have a few works on this, but now we want to do this. We want to solve a more complex problem, which is using federated learning, which is not that complex, but the complexity comes with missing time points and shifts and variations across temporal acquisitions, which means different hospitals acquire different data with different domain time shifts. And how can you learn to predict with missing time points, missing observations, et cetera, between hospitals having cross-sectional data? It's a very difficult, it's a challenging problem. Like even theorizing it and thinking about it is a very interesting problem. Actually, what I'm hoping that we can also theorize this and make it more like robust, but this is a very preliminary work, so which was published recently. So here, how did we formalize this problem? So first, let me explain this. We had already an existing model that we designed to predict a GNN model, a graph neural network that we designed to predict the evolution of brain graphs. So that's already there. So what we have here, we have hospitals. Look, guys, we have different hospitals. Each hospital acquires its own data, and we have different time points. So an ideal hospital would have all the time points, which means all of them will be ones, okay? But some hospitals will acquire, like all time points, 2 consecutive time points, like here, these 2 are acquired. but the next hospital might have this time point, the next one is missing, this hospital missing, next existing. And the fourth scenario here, we have 4 scenarios, 2 consecutive missing time points. How are you going to teach, like a hospital with a particular data to do prediction, and it has only acquired 1 time point, has no data to train on? Do we agree on that? So let me explain a little bit more. So here, who knows what federated learning is? Okay, very few. Okay. So basically, federated learning, let me give you a brief introduction. So what we have different hospitals or clients. Each hospital collects its data. So data, for example, we have 2 classes. We can have typical brains and brains with Alzheimer's disease. So the typical way of training models is like each hospital will work individually, independently. You train an SVM classifier, for example, on your data, okay? And then you do your classification. A second hospital in, let's say this one is in Morocco, the other one is in China, it will train on its own data set. The other one is in the UK, it will train on its own data set. So they work independently. What does it mean? It means all of these hospitals, they have diversity in their data sets, but they're not sharing their data sets. Everybody is training their personal model, keeping it to themselves. There is no sharing, okay? So the strength or the idea of federated learning or decentralized learning has emerged over the past few years. And the key idea is that, well, if you don't want to share your data, it's okay. Don't share your data, keep your data. I know there's a lot of ethics that comes and issues with data sharing. So just give me your model. So what does it mean? It means I'm training an SVM classifier, learning my W mapping, my hyperparameters, like my model. And then when I'm communicating, every single hospital shares or sends their model to this server, okay? So the model, imagine the model is your hyperplane. So it's moving. So hospital 1 got this hyperplane, hospital 2, another hyperplane, etc. So because you're collecting information, because you're from different diverse data sets that are not inherently shared, you're diversifying inherently your models. So you're having different models that capture variations in your data. So at the end, after all of these hospitals share their model weights, you're going to aggregate them. So you can average them. So after you average them, then you're going to broadcast them back to the hospital. So the hospital here will get the average model that was used, that has benefited from all these data sets, but without sharing the data sets, okay? And there was like the state of the art in federated learning, it shows a large improvement and boosting in local models when they are trained in a federated way, which means you are able to better generalize to unseen data. So here in this example, we designed a novel federation method. So going back, so we had, let me just go one step back. So here we trained a GNN model. So this is very simple. You guys now know you have an input graph and the output is another graph. So you map a graph onto a graph from time point t to time point t plus 1, okay? However, this GNN model, depending on the scenario that we're having, whether the current hospital has existing sequence to 2 consecutive points or not, it will change its role. So for example, in the worst case scenario where we're training this GNN model for this hospital on this data, it will act as a self-generator, which means it's like almost identity map. So it's gonna map, the original time point over and over and over again until it gets a new observation, okay? So for these 2 scenarios where we have an existing time point and a missing one flipped, so for this one, it will act as a generator. So because basically this time point right here had an existing one before, and for this one it will still act as self-encoding, but whenever the next time point is missing, it will self-encode. If the next time point is existing, it will generate. So that's the idea, okay? So once it's self-encoding, it's acting as auto-encoder, which is just identity mapping. Other times it's generating, which is training this function to map xt onto xt plus 1. But you might ask me, okay, if I'm doing this, how is this hospital learning? It's just self-mapping, right? Just taking, how is it going to predict the evolution of a graph for a particular subject? So the key here is in the federation, because every single hospital, this hospital has 2 missing time points. But in the federation round, it has taken the model from the hospital that do have the time points, right? So it's averaging, it's aligning, it's kind of rectifying its model by learning from the strongest hospitals with the available data. And through this aggregation process, through this federation process, all hospitals are getting normalized in their learnings, despite of the variation in their existing time sequences in the original ground truth data that they're having, okay? So basically, this is the key idea. I'm not going to go into details, but if you guys are interested, you can read the TMI paper that got published recently. And we used 113 subjects, so you guys can see we have a small data set, 5-fold cross-validation, and we compared against different approaches. So I'm going to show this. So first, we have the 4D GNN, which is a regular GNN without any federation. So we have a very large error here for time point T1. Actually, we had 3 time points, and we're predicting 2 time points. From T0, we're predicting T1 and T2. So without federation, you have a very large error. Now, when you use 4D Fed GNN, 4D federated GNN, which is, you know, like just with aggregation, you know, just aggregating basically the models, we got a very good decrease in error. So you can see a large improvement here, and it's statistically significant on this real data. And we have replicated this on largely simulated data sets with many time points. So the paper is more extensive. And the last one is what we propose is the 4D Fed GNN plus. So the plus here is actually, we introduce an ordering in which the hospitals exchange models. So it's more complex. I didn't talk about that. So basically, if I have all my time sequence, I will be communicating my model to everybody. But if I'm the poorest one, I will be communicating less. So we had an ordering of the way the federation is happening, where the strongest is communicating to the poorest, basically. And this has improved the results also for T1 and T2. It's remarkable. You can see that with our new federation strategy, with the ordering strategy, we got better results. So these are just overviews of 3 different cross-domain, cross-dimensional prediction. So we talked about domain. Hello? You guys are still awake. Okay, good. Time and resolution. Okay, so the data set is available for the time dependent one. So if you are interested, we have organized a Kaggle competition that was also published. This was by my undergraduate student at Istanbul Technical University. It's a simple paper, it's not fancy, but the data is there, and we use just machine learning, by the way. I told them, like, no deep learning, just let's try to solve this problem using conventional machine learning and see which state of the art we will be performing, if we're going to outperform state-of-the-art methods. So the competition is available. I think I'm not going to talk about integration because we don't have time. So I'm happy. This is actually a very cool project. This is the integration where you take multiple tensors and you try to integrate them into a single matrix like this, a fingerprint. So we try to discover a fingerprint of a population. And yeah, so this work is fully novel. We outperformed the Nature 2014 paper, Nature Methods, and that was state-of-the-art method in integrating graphs. The only thing is that we use geometric deep learning, by the way. So this was the first deep graph normalizer, deep graph network that collapses a set of tensors into a single matrix. If you guys are interested in learning about the work, there's a long video online with all these animations detailed. So feel free to look at this graph integration. So why this is interesting, I'm just going to say why this is interesting. So there is a lot of technical novelty here, but imagine that generally what we do, we take large data sets, we try to diversify our data. We're looking to cover the spaces of cats and dogs, and then we train our classifiers. But here we're reversing the thinking. So we're saying we can collapse if we have a good representation, we can collapse all dogs and all cats into a representative image, A and B, and learn a very good generalizable classifier. So that's what we're doing here. We're collapsing the data into a representative point through data fusion, and then we're learning by using this template. The second thing is we we took, for example, Alzheimer's disease and typical subjects. We took also autistic data and typical subjects. And what we did, we trained this DGN, deep graph normalizer, generated what we call this template, the CBT, connectional brain template for autism, connectional brain template for typical subjects. And what do we have here? Two matrices, okay? So we have two matrices. So if you compute the difference between these two matrices, what will we get? If you have autistic connectivity brain and you have typical connectivity brain, and you can calculate the difference matrix between these two, what will we spot? Brain regions, but brain differences, right? So biomarkers, we will spot biomarkers, like what marks the difference between this population and the other one, okay? So what we have shown that by simple matrix subtraction, we can reproduce 80% of the biomarkers that are found by complex deep learning models, simply by subtracting matrices, okay? So a whole lot to say, but this is the idea of using graph fusion for mapping populations and doing classification, regression, down learning tasks. Okay, so I'm going to just go over this, not cover it. GNN reproducibility is a very interesting topic, though. Now, one last thing, just to wrap up quickly, guys. I want to talk about the RISE MIKAI. So this is, MIKAI is the top conference in medical imaging and machine learning. So if you guys think about NeurosCience, of course, it's generic, ICL are highly generic. But when it comes to machine learning, designing novel machine learning solutions to medical imaging, medical data, this is class A1 conference. Unfortunately, the number of submissions coming from low middle income countries, there are only 3%, and this is just submission. Okay, so the number of submitted papers not accepted. So you guys can see for 2020, these are also the submissions, and you can see that Africa is not there, Latin America is not there, Southeastern Asia is not there. So unfortunately, there isn't representativeness of these countries in top medical imaging healthcare conference, which means when a pandemic strikes, half of the world will struggle somehow. Okay, so kind of we need to empower, we need to kind of do knowledge transfer, we need to build collaborations, build bridges, do things together, empower one another. And so yeah, just sharing more data. If we try to geolocate the top researchers in the field, in 2019, only 4 countries out of 103 got their papers accepted. Yeah, so very low contribution. So what we want to do, we want to build this network to better handle global health crises. There is an absence of a global health network to collaborate, find solutions together as a world as a whole. So what we want, I co-founded this with Dr. Shadi Barkouni from Technical University of Munich. I'm currently the president, so we're offering lots of training. I'm just gonna give you an idea in a bit. So we aim for inclusiveness, empowerment, building networks, paving the way for future stars to rise from those countries, increasing their contributions to these top conferences and research, maybe industry one day too. So we have also industrial partners. So we have lots of upcoming events. So if you subscribe, if you just Google RISE MIKAI, you'll find the website, and then you just go down and fill out a Google form. You'll be able to receive just a newsletter about our events, what we're organizing. So starting from January, inshallah, we're gonna organize a bi-weekly journal club where you will attend the Zoom meeting. You need to read the paper beforehand. You'll come and we'll dichotomize a paper 0 to 1, literally, and you'll get exposed to the ways of reasoning, why this is an interesting problem, the rationale, all these questions that people ask when you submit to high impact journals and high, top conferences, why your paper is not there. We're going to teach you these methodologies of thinking, arguing, and also defining hypotheses through paper reading. So it's not just a regular journal club. Okay, so we have also lots of things we're organizing: hackathon, summer school, winter schools. So recently we've organized this. I've coordinated the winter school last weekend. The weekend before that, and we had keynotes. It was a 3-day event for 3 hours. It includes an introduction to, for example, image registration, medical image registration, plus a tutorial. And it was really vibrant. It was highly interactive. Like, this event is amazing. We had people from Nepal, Thailand, Senegal, Algeria, Tunisia, so it's Guatemala. It was very, very diverse. And that thing made me really, happy. So to become, if you want to become an ambassador, if you want to become an ambassador of your country, if you want to contribute, if you want to learn, you want to grow or help, volunteer, this is the QR code. Feel free to fill out the form. So there is another network that I really want to advertise. So all of these are free events, guys. Okay, so this is the MIKAI, African AI, which is also focusing on intelligence, AI with application to biomedical imaging. They offer a lot of seminars. So we started this. This is the organizing committee of MIKAI 2024 for the first time in its history, and since its 37th edition, it's going to come to Africa. And it will be in Marrakesh, which is wonderful. So we're looking forward to hosting MIKAI here in Marrakesh. We are organizing also an MIKAI Africa summer school, and we offer scholarships. It's fully funded. You guys just need to apply and come, learn, attend, go back home, okay? So how to get your paper ready for MIKAI 2024, how to submit to top journals, how to get paper through. So these are things we're doing. One last thing, if I'm allowed, we're also, I'm part of IX. This is Imperial X, a very cool building and stuff like I have joined recently. We're providing 20 postdoctoral fellowships. If you guys have a good CV, a good profile, you're interested, I'm happy to support and I'm happy to help and give advice, okay? So this is, the Schmidt AI Futures. It's a very prestigious fellowship. There is an independent panel, have nothing to do with them, but I'm happy to help if you want to consider, applying for AI, applying for a fellowship in AI with application to medical imaging. Yeah, that's pretty much it. So I want to thank all of my students over the years. This was a recent hangout, and thank you guys for listening.
Thank you very much for your talk. Are there any questions?
Thank you so much. I'd be interested in for the Federated Learning project. Were there any issues with like batch effects? I know for MRI really depends on the scanner, the calibration, and everything. Are you working on the graph?
We're working on the graph directly. So we are agnostic to the way the data was acquired originally. So we are only interested in the graphs and the graph data distribution. So we start from our starting point in all of those is graph adjacency matrix.
And the graph is invariant to those changes in the images?
No, it's not. That's another problem to solve. A very interesting question, but it's not, unfortunately. Like even if you change the processing algorithm, you might get a different graph map, which is not good.
And have you agreed
in the literature?
That the hospitals use the same graphing algorithm?
So for now, we're using the same algorithm. Yeah, so we're trying to standardize that, but it's not sufficient. I think we need to define specific protocols on how to standardize that in the future. Thank you. Ensemble learning is a very good question. Ensemble learning, you need to use all the data, you need to have access to the data. But this one, you don't have access to the data. So every model is not able to see the data of the other guys. And also ensemble learning, if you have multiple types of learners, if you use SVM and base classifier, you cannot add the parameters. You need to use the same model for each hospital. So federation, basically one single model distributed across different hospitals to train on their local data sets versus ensemble learning, one data set, different models. So it's the reverse way of doing things. So we order the models based on, that's a very good thing, because when you federate, you exchange your model. So I'm a hospital with all time points, and I have next to me a hospital with less time points. It would make sense for me to benefit, I'm the weak hospital. Let's say I'm the hospital with missing time points, many of them, and the next guy has many time points. It makes sense that I take information from him first before he takes it from me. because he has the right model. Like, you know what I mean? So the flow should be directional. It should not be adirectional. Yeah. Cool.
Thank you for your interesting presentation.
Thank you.
I have a question about cross-domain.
Crossdomain, yeah.
Yeah. The first to use just for
Just for?
no.
For nodes, it's just an example. It's an example. But for real, we use 35. The real data set had 35 nodes, and the output has I think 160. But you can customize the network. You can customize the network. So you can map any time, you know, NR into NR prime, for example. Yeah. Cool.
No more questions? Well,
Thank you.
very much.